This is a Tektronix 15OC cable tester. It was developed by the cable TV industry in order to identify problems with coaxial cables, but we can use it to measure the dielectric constant of soils and to determine the water content. And so this is a commercial waveguide that's used for the time domain reflectometry measurement. This can be used with the cable tester, and we can also, though, develop our own designs for waveguides. This is a design that we developed that's intended to be pushed in laterally into the side of a borehole. So the base of it is sticking out laterally instead of out this way. So it gives you a good bit of flexibility. We'll stick with this commercial waveguide, and I'll show you how it's used. We attach it here, and then turn the power on with this knob, and it has a screen that you need to read to get the measurements. So I'm going to zoom in on the screen, but what I'll do is take this waveguide, put it in some water. So this will work like a calibration run. We're going to measure the dielectric constant, and since we know the dielectric constant of water, we should know the value that we should get when we interpret this signal that we see on the screen. So let's zoom in. So now we can see the screen fairly clearly. I'm going to go and do this test. I'm going to put this waveguide into some water, and we'll get a signal. So I've just turned this on, and the first thing that we do, I guess I'm going to take it out of the water and just have it sit on the ground here. And so the first thing we do is we need to find out where the end of the wire is and where the waveguide is. So we'll use this knob to scroll with the cursor. You can see the cursor moving across the screen, and we'll scroll over to the right until we find the end of essentially the effective end of the wire, and it's right here. You can see where the signal jumps up. It's reacting to the end of the wire, and it's reading out 8.48 feet. So that's the length of the wire, and this device is used to find the breaks in coaxial cable, either a break or a short. And when you're trying to diagnose where that break is so you can fix it, you want to know how far along the cable it is. And so that's why this is reading out in units of feet. And so we can see the end, and it's kind of these squiggles. And what's going to happen is that this waveguide is going to create a distinctive pattern when it enters the water. So as I put it in the water, you can see the signal over on the right side of the screen change. And now it's completely immersed in the water. So I'm going to scroll over here a little bit further, and this signal here where it's flat and then it drops and then it comes back up, that's the waveguide. And this part of the, let's see, right here, roughly right in here is the front end of the wire, or front end of those rods, and this is the back end right here. So what we need to do is measure the effective length of these rods, and to do that I'm going to amplify the vertical scale a little bit. So now we can see that signal from the waveguide quite clearly. And I need to find where the waveguide begins. So I can do that by taking these out of the water. So I've pulled the waveguide out, here it is, and I'm going to put it in. So I've just got the tips of the rods in now, and they're going about halfway in, and you can see this waveform developing, and now it's all the way in. Okay, and so I pull it out again, put it in again. And what happens is that the signal changes where the water is in contact with the rods, but it doesn't change where the rods are in plastic. So what I can do is scroll the cursor along, and I think it's right about here. I think that point, to the left of that point, doesn't change when I put the rods in or out, but to the right of it does change. So that allows me to identify where the rods are first exposed to the water. And then I'm going to find the end of them by finding where the signal first starts to increase out here. And I'm going to get the effective length of these rods according to the cable tester. So to make my life easier, right now it's reading 8.56 feet. And I'm going to reset this by, I turn that knob one click counterclockwise or clockwise, and then I press store, and then I turn it back, and now it should read 0 here. So now when I move the cursor, I'm reading 4.36. So I'm reading in units relative to this point on the to the 0 point that I've just created. So that looks like the point where it first starts to curve up, 4.32. And so that's the effective length that the TDR thinks these rods are. And let me see if I'm going to pull this up off the bottom a little bit. And by doing that, if I raise it up off the bottom, I think I can move this out a little bit further, right to there. So that looks like it's a little bit longer when I pull this up, when I pull the waveguide up off the bottom of the bucket. Okay, and so that gives me 4.4 feet as the apparent length. Now to calculate the dielectric constant, you take the apparent length that the TDR tester thinks the rods are, and you divide by their actual length, and then you square that, and that gives you the dielectric constant. So 4.4 feet divided by 0.5 feet, the actual length of the rods, is 8.8. And then we square that, and that's about 78, which is pretty close to the dielectric constant of water. So we've used this cable tester that was developed to identify problems in coaxial cables, and we've used it to create this waveform that we can read and then determine the dielectric constant. We've tested it first on the dielectric constant of water, and we're getting some pretty good results. So now I want to go and put this waveguide in some soil and get some readings there. So I have this is resting on some soil. I'm just going to push this into the soil right here. And there's the reading. Now the 0 point should still be at the same location. So I go back to 0, remember I zeroed this out, and it's right there. So the 0 point is right as this signal drops down a little bit. Okay, now the wave is not as stable as it is in pure water, but I'm going to scroll along and get the point where it first starts to kick up right here. Okay, I could change my scale here. That would help me get it a little bit more accurately, although it is moving around a little bit. That causes some difficulties. So that looks like about the point where it kicks up. This now reads 1.84. So to determine the dielectric constant, I take that and divide by 0.5 and then square it. And that's going to be, I guess, something like 14, 15. So the dielectric constant is obviously much smaller than water. And we could then take that value and determine the moisture content using the top equation. So this is how you go and use this cable tester. One of the things that's important to understand is how these knobs work. These are scrolling horizontally. This is moving the signal vertically. This is changing the horizontal scale, and this is changing the vertical scale, and you can use this to set the 0 point. So you should experiment around a bit with these knobs to make sure you understand how they work. And it's useful to put the device in some water where you get a very nice clean signal as you're first getting used to how this works. That'll get you started with a good baseline.